Hi again. In this part, we are gonna look the independence. So, in the previous part, we have introduced the conditional probability, right? There's one p probability of A, for example, given B, and we did this to capture the partial information that event B provides about the event A. So the B will provide us some information to calculate the probability of A. So in that point, an interesting and important special case arises when the occurrence of B provides no such information, okay? So it will not change the probability of the A. So knowing the B occurred or not will not change the probability of A. So in this case, the probability of A given B will be equal to probability of A. So it will not change anything. When the above equality holds, we can say that A is independent of B, or vice versa. We can say B is independent of the B. And also, I can rewrite this formulation as, the P A given B is equal to P A intersect B divided by PB. So I can rewrite, and this is equal to PA, and I can write this one, right? Probability of A intersect B is equal to probability of A times probability of B. So finally, we can say that A and B are independent events if the probability of their intersection is equal to the probability of A times probability of B. So individual multiplication, if the individual multiplication is equal to intersection of that events, we can say that these events are independent. And this equation is also be used when the probability of B is equal to 0. If you remember, it will make the probability of A given B undefined. And also, this is same for the A and B complements. So you can check this one from the book questions, and you can test yourself. Okay, so I can say that if an event doesn't give any information about the other events, we can say that these are the independent one. Okay, so let me give you an example. We have a four-sided die. Okay, and let's say the event A is the results of the first row, and it will be I, and let's say the event B is the result of the second row. Okay, so this can the probability of A will be 1 over 4, right? So we have 4 different values, and the same probability of B will be 1 over 4. And let's say, let me check the other, let me check the correct question. Okay, here in the A intersect B, let's say the results of two rows, let's say this is a J as IJ, right? So the probability of A intersect B is going to be 1 over 16, right? Because 16 different pairs can be results of 2 rows. So what we say that if A intersect B is equal to PA times PB, we can say that these events are independent, right? So what is the probability of A intersect B is 1 over 16 and 1 over 4 times 1 over 4, and we hold this equality. So that's why we can say that this these two events are independent. Okay, so let's look at the same thing but different events. Okay, let's say A is result of first row is 1, and let's say the result of second row is, I think that was let me check it. So, and not the results. Let's say this is a sum of 2 rows of 5. Okay. So the probability of A is 1 over 4, right? And the probability of B is, so it can be take 1 4 2 3, sorry, yeah, 2 3, and it can be 3 2 and 4 1. So am I right? Yeah, so that's the probability of B will be equal to one, again, 1 over 4, right? It is coming from 4 divided by 16. This is all the pairs, and this is the pair for the event B. So, and let's look at the PA intersect B. In this case, we need to look the results of 1 4, right? Because it will be intersection of the two events, and the first event is the result of first row will be 1, and if this is the 1, the only value the only value can be 4 in the second row, so this is the only intersected point. So, and the probability will be 1 over 4, right? So let's check the equality, and the PA times PB, this is a 1 4, and so this is, sorry, the 16, there are 16 pairs, and only one pairs hold our situation, the events, times 1 over 4, and is it equal to probability of A intersect with B? Yes. So I can say that these two events also independent. And let's clear this one, and not this one here, and let's check another example. I think, yeah, let's check this one. In this case, let's say A is the max of, or the, let's say, mean of rows is 2, and let's say the max of roles is 2. So what pairs uh, what pairs falling into the group A, I mean event A? So it can be 2, 3, right? And 2, 4, right? Am I right? Yeah, 2, 2, 3, and 2, 4. This is an event A, right? And let's say, yeah, it is, let me write. And also 2, 2, right? 2, 2. So the B is 2, 2, which is the maximum one, 2, 1, and the 1, 2, right? So in this case, the max of this pairs is 2, and in this case, the mean of this pairs is 2. So the probability of PA is um, is 3 or 16, right? And the probability of B is also 3 of 16, right? So let me check myself not to do any mistake. Um, I think we did a mistake here. Sorry, I forgot to write the things. Let me try. Let me write the 2, 3, 2, and 4, 2 again. Okay, so I forgot this pair. So, and this will be 5 over 16, and the probability of B will be 3 of 16, right? So let's look at the A intersect B. That means the minimum of the rows will be 2, and maximum of row will be 2. In this case is valid only for this one, right? 2, 2. So the probability of A intersect B will be 1 over 16, right? Because there are 16 pairs and only one of them is only one of them belongs to A intersect B. So is it equal to 5, 16 times 3, 16 is equal to 1 over 16? No. So I can say that these two events is not independent. Why? So again, if you look at the definition of the independence, we say that the events will not provide any extra information about the other events, or in other words, it will not change the probability of the other events, right? But in this case, the minimum of the rows is 2, and maximum of the rows is 2, is actually give some piece of information about the other events. That's why they are not independent. Okay, so the independence is like that. So let's continue to another slide. So there is another term here, which is the conditionally independent. So we say that A and B are conditionally independent events given another event C, with the probability of C is greater than 0 if we can yield this equality. So probability of A intersect B given C is equal to probability of A given C times probability of B given C. So this is the case, but how we can prove that one? Okay, so let's rewrite this part. Let's rewrite this part by using the definition of the conditional probability. So actually, this part is equal to A times B times C, right? And so this is a probability and probability C. Okay. So then use the multiplication rule to rewrite this part as, which is equal to probability of C times probability of B given C times probability of A given B intersect C, right? Probability of C. So first we rewrite this part by using the multiplication definition, and then we rewrite this part by using the multiplication rule. So do it yourself, just test me, okay? And this is equal to this part, BAC, A given C times B probability of B given C, right? So these are eliminated and these common factors are eliminated, and we just remain with this part. So which is, let me change the color. This is actually the probability of A given B intersect with C is equal to BA intersect. So how can we interpret this one? So this part, the right side, is the probability of A given C, right? And in this part, probability of A given B intersect with C. So occurrence of the B didn't change the probability of A. Okay. So this is an important. Occurrence of the B didn't provide any piece of information, so that that didn't change the probability of A. So that's why, if this is true, this equality is true, we can say that these events are conditionally independent. Okay, so let's continue. So also we can generalize this these formulations for the n events. Let's say we have some events from A1 to AN, and they are independent, or you can call it mutually independent, jointly independent, whatever you want. If for every subset S for the indices from 1 to n, we have the intersection of those events is actually the product of the events. Okay, so if this is the, for example, three events, we can say that the probability of A1 intersect A2 intersect A3, we can say that, which is probability of A1 times probability of A2 and probability of A3. Okay, so we can generalize this equation, this equality, by using this formulation. This one, okay, we can generalize this thing to check the independence of more than two events. So for the case of the three events, let's say three events. So independence amounts to satisfying the following four conditions. So in words, we can say that. So in a summary, we can say that if three events satisfy these four conditions, we can say that they are independent. Okay, they are independent. So this first three actually check the pairwise independence. So checking this one, but not checking the last one, cannot ensure that these three events will be these three events are independent. So that's why you have to check all of them, not the three of them, not the last one, but all of them. So, and as I said, the pairwise independence doesn't imply the mutual or the joint independence. So, for example, A1 and A2 can be independent, but that doesn't mean that A1 and A2 and A3 is the independent. And also the mutual or joint independence imply the pairwise independence by the definition. So if you say that the A1, A2, and A3 are mutually independent, we can also say that A1 and A2 independent, A1 and A3 independent, A2 and A3 independent. So again, just checking this three or the last one is not enough to check the independence. Okay, you have to check all of them. So let's look at some example to make more concrete your understanding. Okay, so consider two independent fair coin tosses, and the events are the H1. The first toss is head, so it can take head and head and head and tail, right? And let's say the H2 is second toss is head. So it can be tail head and head, right? And the D is the two tosses have different results. So it will be head, tail, and tail, head, right? So you can check these events independency by looking at this one. The first one is, let's check. The probability of A1 intersect A2 is equal to probability of A1 times probability of A2. Okay, what's my omega first? Omega is head, tails, head, heads, tail, heads, and tail, tail, right? So the probability of H1 is 1 or 2, right? And the probability of H2 is also 1, 2. And the probability of D is also 1, 1, 2, right? So the first one is the probability of H1 intersect H2. So which is only hat and hat pairs satisfy this condition, right? This intersection. So that's why the probabilities will be 1 over 4, right? So there is only one pair, and out of 4, 1. Is this equal to probability of H1 times probability of H2? So let's check. This is a 1, 2 times 1, 2. So yes, 1 over 4 is equal to 1 over 4. So we can say that H1 and H2 pairwise independent. So let's check the other one, H1 and D. Let's check that one, H1 and D. So again, the intersection of the H1 and D is head and tail, right? So, which is 1/4. And multiplication of the H1 and D is 1/2 times 1/2 is 1/4. So we can satisfy the second condition. So we can say that H1 and D are the pairwise independent. And the second one, the third one is H2 and D, right? So what is the common point here? Tail and head, only one pair. So the probability of H2 intersect D is 1/4. And multiplication of the individual probability is also 1/4. 1/2 times 1/2 is 1/4. So also we can say that the H2 and D are the pairwise independent. So now let's look at the last one. So intersection of all three events. So we need to look at the probability of H1 intersect H2 intersect D, right? So is there a common point there? I think no, right? So TH, no, HT, no. So the common point, the intersection of this three event is 0, right? Let me double check. So I think our omega is correct. Yes. So yes. So there's no intersected point. There is no common point. So the probability of the intersection of all three events is 0. So what is the PH1 times PH2 times PH, so PD is 1/4 times 1/4 times 4 is equal to 1/8, right? So I cannot say that these these events are mutually independent, right? Because I didn't satisfy this equality. So that's why we have to look at all the conditions here. We have to check all four conditions to check the satisfying of the independency of the events. Okay. So let's look at another example. In this example, we have two independent roll of fair six-sided die, and we define some events. The first roll is 1, 2, 3, and the second event, the first roll is 3, 4, 5. Okay, and the event C is the sum of the two rolls is 6. So let's first calculate the probability of A, okay, which is 1/2, right? There are three there are three members and out of 6, and the probability of B is also 1/2, right? So the sum of the two rows is 9. So let's look at C. C can take the values. So C can take 36 different values, but only some of them will satisfy this this condition, right? And it can be 3, 6, 4, 5, 5, 4, and 6, 3, right? So it is the probability of the C is equal to, right? Am I right? I think yes. Okay, so let's check the first condition, the A intersect B. So the A intersect B is 1/6, right? Because there is only one common point, and the probability will be 1/6. But the individual multiplication of the probabilities of that events is 1/4, right? 1/times 1/2 is not equal. So I cannot say that these two events are pairwise independent. Okay, let's check the A and C. So there is no common point, right? Because A will get only the one value, right? And let me double check this one. I think there is a mistake here. Oh, so n times. Okay, so okay, the first roll will be 3, and the common point is only this one, right? Only this one, only this one's first number is 3. So that's why there is only one common. So there is only one pair. So that's why the A intersect with C is 1/36, right? But individual multiplication is, I mean, the PA times PC is 102 times 4/16, right? This 4 is coming from this one, the number of elements in C and the number of elements in sample space. So this is a 2/36, but the A intersect with C is 1/36. That's why we didn't satisfy this condition as well. So I cannot say that A and C are pairwise independent. So let's look at the other one, which is a BC, right? BC. So in this case, B and C, what is the B? The first roll is 3, 3, 4, and 5. So 3, 4, and 5, right? There are 3 pairs. So the probability of B intersects C will be 3 or 16, 36, right? So individual multiplication will be, let me clear this. Will be the probability of B times probability of C, which is times this one, right? And this is not equal to this one. So that's why I cannot say that also the event B and event C are pairwise independent. Okay, let's check the last condition, which is the probability of A intersect with B intersect with C. Okay, so in this case, which is, let me rewrite the event C, which is a 3, 6, 4, 5, 5, 4, and 6, 3, right? So intersection of the all events, actually, the first event is this one, right? Only one. This one. So, which is actually the 1/36, right? And individual of them is 1/2 times 1/2 times is, right? So this is the same, right? Even if these are equal, because these the first 3 conditions are not satisfied, we cannot say that these are the mutually independent, and also they are not pairwise independent. Okay, so this is the concept of the independence, and you can double check yourself by solving some problem and looking for the corresponding parts of the book. So, and we will continue to probability with the random variables in the next lecture. But I just want to tell something, because I don't remember if I said before. If you think that the disjoint events are disjoint events are independent, it's wrong. Okay, that doesn't mean that. I mean, the disjoint events, actually they are not independent. Okay, so this is a case. Please keep this in mind, because usually people confuse about that one. I mean, they thought that if the events are the disjoint, they say they are independent. No, it's not. If that events are not, if the events are disjoint, that's mean they are not independent. Because I mean, let's say, let me find an example, and it will be more clear. Let me find it. Oh, okay. Actually, we solved the question. Do you remember the first question we solved it? There is a four-sided a pair die, and you know, we will make the two roll in the, we define it 2 events, the event A and event B. So we can define the events in the part C. The maximum of 2 rolls is 2, and the minimum of 2 rolls is 2, right? So actually, the rolling that die in each time are the disjoint events. But as we prove in the solution, we say that they are not independent. Okay, so that's why we cannot say that. This is important. We cannot say that if two or more events are disjoint, we cannot say that they are independent. Okay, please keep this in mind and uh, check check the corresponding parts in the book in chapter 1. Okay, so I will see you in next lecture.